Imagine for a second, right, that you are tasked with managing the construction of a massive, towering skyscraper.
Oh boy, that is a pretty big job.
Right. And to ensure the structure is fundamentally safe, you deploy this automated fleet of highly specialized drone inspectors.
Okay, I'm with you.
So their job is to scan, every single rivet, beam, and pane of glass. It is essential, completely non-negotiable work. But as you review their logs, you notice a systemic flaw.
Let me guess, they're wasting all their time on logistics.
Exactly. The drones are spending 90% of their processing power just establishing a connection to the central server, authenticating their credentials, and formatting the header of their reports.
Wow.
Yeah, only 10% of their compute is actually spent analyzing the structural integrity of the steel.
Well, I mean, the overhead is completely eclipsing the actual payload of the work at that point.
Exactly.
And in a scenario like that, the sheer volume of redundant logging makes it incredibly difficult to spot a genuine structural anomaly, right? Like when it finally does appear in the data.
Yeah, you are generating noise instead of signal.
Precisely.
Well, welcome to the reality of modern software development, because that exact scenario plays out every single day inside our automated test suites.
It really does.
So today, we're taking you on a deep dive into a very specific, highly focused piece of source material. We're looking at a developer journal entry titled Notes on Haskell Programming, Part 185.
Written by an author named Ang.
Right, Ang. And this was published on July 13th, 2026.
The entry itself is a pretty concise snapshot, but it captures a universal inflection point in the life cycle of any maturing code base.
It really does.
It documents the transition from just brute force test coverage to sustainable, architecturally sound test design.
Yeah, and our mission today is to deconstruct how a few clever lines of code can completely slay the monster of boilerplate in programming test suites.
Say the monster, I like that.
And even if you aren't writing Haskell day in and day out, the mission here is to extract the universal coding philosophy behind simplifying complex systems.
Right, because the principles apply anywhere.
Exactly. Okay, let's unpack this. Because reading someone's programming diary is like popping the hood and looking at the raw, unfiltered engine of the digital world.
Yeah, you get to see the actual friction a developer experiences, not just the polished final release.
And that friction is so important.
It's the catalyst for good engineering. In software development, the initial phase is almost always about just getting the logic to work, right?
Yeah.
Just proving it works.
Right, just make it pass.
Exactly. But this journal entry represents that subsequent vital realization where the developer recognizes their testing strategy has become unsustainable.
It's the pivot toward elegant abstraction.
Spot on.
So let's start with the specific friction Ang is running into here. The journal entry kicks off by discussing the consequences of adding lots of test cases.
Right, to ensure proper coverage, as they say.
Yeah, and Ang notes that to ensure that coverage, they've inadvertently ended up with this massive accumulation of repeated code. There's this wonderfully poetic line in the text.
Oh, I know the one.
Ang refers to the copy and paste and slightly tweaked test code we've been writing all these moons.
All these moons. I love that. It conveys this deep sense of fatigue,
It really does.
It highlights how technical debt doesn't happen overnight. It is a slow geological accumulation of tiny compromises over months or years of development cycles.
Yeah, well, think about writing test coverage like doing your laundry. It is a fundamental requirement if you want to, function in society.
Let's hope so.
But copy-pasting your test code is akin to avoiding the washing machine entirely.
Okay, how so?
Well, instead of cleaning your dirty socks, you just go to the store, buy a new pack of identical socks, and slightly tweak which drawer you stuff them into.
Oh, wow.
Right. Over all these moons, your house becomes a labyrinth of overflowing sock piles. You achieve the goal, like you always have clean socks.
But the ecosystem of your house is destroyed.
Exactly. My read on this is that developers don't set out to write bad test suites.
No, of course not.
They just prioritize the immediate safety of a passing test over the long-term architecture of the test suite itself.
What's fascinating here is the psychology behind code maintenance, specifically in testing environments.
Right.
I mean, production code gets refactored mercilessly, but test code is often treated as a second-class citizen.
That is so true.
When a developer is under deadline pressure and needs to verify a new edge case, the path of least resistance is to find an existing test that structurally resembles what they need, duplicate it wholesale, and mutate a single variable.
And boom, the test passes.
The test passes, the pipeline stays green, and the developer feels productive. They don't realize they are increasing the maintenance burden for whoever has to read that file 6 months later.
And Eng points out the specific technical pain point driving this copy-paste behavior in their Haskell codebase. They're dealing with functions that return an either type.
Right, the either type.
Yeah, and because Haskell forces you to handle both potential outcomes, the right success case and the left error case, every single test requires a bulky case statement.
Just to unwrap the result.
Exactly, before this actual assertion can even happen.
And that verbosity becomes the enemy of readability. I mean, if a test is 20 lines long, but 18 of those lines are just the mechanics of unwrapping an either type.
Yeah, and handling a generic failure state.
Right, then the actual intent of the test, the specific business logic being verified, it gets completely buried in the boilerplate.
Which brings us to Eng's pivot. The proposed solution is to cut through this noise by creating short helper functions.
Powered by pattern matching.
Yes, powered by pattern matching, completely replacing those manual case statements inside the individual tests. Now, wait, hold on.
Why?
I have to push back on this premise just a bit.
Okay, let's hear it.
Isn't creating new helper functions just moving the messy boilerplate to a different room and shutting the door? I mean, to go back to my laundry analogy, if you take all those piles of dirty socks and shove them into a spare closet.
The house looks cleaner to a visitor.
Right, but you haven't actually solved the sock problem. You just have a localized disaster area.
Yeah.
How does pattern matching actually reduce the structural complexity of the code rather than just obfuscating it?
That's a fair question. But hiding a mess and eliminating a structural inefficiency are two very different concepts, though they are frequently confused in software engineering.
Okay, explain that.
Well, if Eng had just written a massive, unwieldy script to hide the case statements, you would be right. But pattern matching in a functional paradigm isn't merely syntactic sugar for hiding if-else branches.
It's not.
No, it changes the way data flows through the application.
Okay, let's use a networking analogy here. A traditional imperative case statement is like writing a massive sequential if-else script for a security guard inspecting data packets.
Right.
The guard has to halt the packet, read the header, sequentially check it against a list of 50 rules, and then manually carry the packet to its destination.
Which is terribly inefficient.
Yeah, writing out those instructions for every test is tedious and prone to human error. Pattern matching, on the other hand, is like installing a hardware router.
Oh, I like that.
The router drops the packet into the network, and the packet's own structural signature dictates its path.
That captures the mechanics perfectly. By utilizing pattern matching inside a centralized helper function, Eng isn't just sweeping the case statements under the rug.
Right.
They're defining the shape of acceptable data once. The rest of the test suite no longer needs to instruct the compiler how to unwrap the either.
It just tosses the data into the function.
Exactly. And the structural routing handles the rest. This creates a composable pipeline, which we see clearly in the actual diff Eng provided.
Yes, let's look at the actual code changes.
Yeah.
Because seeing the implementation reveals the elegance of this approach. Eng introduces two specific helper functions.
Let's start with the first one.
Right. The first is assertRight. The type signature shows it takes an either EA, representing our potential error or success, and it also takes a function written as arrow expectation.
The inclusion of that second argument, the function, is where the real power lies.
Yeah.
Yeah, this is a higher order function. AssertRight isn't just a static check. By passing a function into it, you are delaying the execution of the subsequent test logic.
Here's where it gets really interesting to me. You are effectively telling assertRight, I am handing you a sealed envelope.
Okay.
If and only if you open this envelope and find a successful right value,
Right.
I want you to hand that value off to this next specific piece of logic.
It completely decouples the act of unwrapping the data from the act of testing the data.
Exactly.
That decoupling is the core achievement here. If the pattern matches right X, it applies the provided function to X seamlessly.
And if it doesn't?
If it matches the left error pattern, it immediately short-circuits the pipeline. It triggers an expectation failure and, crucially, calls show error.
Right. It dynamically extracts whatever the specific error payload was and displays it.
Yes.
Now, contrast that with the second helper function Eng built, assertSuccess. This one is designed to handle a parser result.
Right. A different type of data.
Yeah. If the pattern matches success X, it applies the function, just like assertRight. But if it matches literally anything else, which Eng represents with a wildcard underscore in the code R,
The catch-all.
All right, the catch-all. It triggers an expectation failure with a hard-coded static text string. Expected parser success.
The divergence and error handling there is a fantastic detail.
Isn't it?
It reveals a developer making intentional decisions about signal-to-noise ratios in their logs.
Yeah, my read is that with assertRight, which handles general logic execution, you desperately need the specific error string.
You need to know why the database query failed.
Or why the user authentication was rejected, exactly.
Yeah.
But with assertSuccess, you are dealing with a parser. The context is entirely different.
Absolutely. A parser generally does one thing.
Yeah.
It consumes raw text and attempts to build a structured syntax tree. So if a parser fails, the contextual failure is almost always obvious the input string was malformed. You don't necessarily need a custom, deeply nested error message tracing the exact character failure if your only goal in that specific test is to verify the parser accepts a valid configuration file.
Right, a generic expected parser success is sufficient signal.
Exactly.
And both of these helper functions share a critical foundation.
Yeah.
They both route their failures through the expectation failure function provided by the test HSpec library.
HSpec, right.
This feels like a strategic choice rather than just a convenience.
Oh, it is entirely strategic.
Right.
When you allow developers to copy-paste test boilerplate over all these moons.
You also allow them to invent a dozen different ways to fail a test.
Exactly. One developer might use a standard error throw, another might log a custom string to standard out, and a third might use an assertion library from a completely different package.
Which creates an absolute nightmare for the team maintaining the CI/CD pipeline. When the build fails, you have to dig through the logs and manually parse 4 different formats of failure messages just to figure out what broke.
Centralizing the failure reporting through HSpec eliminates that fragmentation.
It standardizes it.
Yes, assertRight and assertSuccess guarantee that no matter what logic fails deep inside the test suite, the output will conform to the exact standardized format expected by the testing framework.
It makes the automated reporting predictable and machine-readable.
Exactly.
So Ang has effectively addressed the logic bloat. The repetitive unwrapping of either types is gone, replaced by these elegant, higher-order sorting pipelines.
But the diff in the journal entry reveals a second layer to this refactoring.
Right, because the logic was only half the problem. The other half was configuration.
Configuration drift is the silent killer of test suite reliability.
The second part of Ang's diff shows the extraction of something called default args, which is of type args. Ang explicitly notes that this baseline configuration had previously been duplicated across several different test files.
And that's dangerous.
To put this in perspective for anyone listening, imagine trying to regulate the temperature in a massive office building.
Ah, the thermostat problem.
Exactly. Consider the alternative to a central system. If you have a manual radiator dial in every single room of that office building, what happens when the seasons change?
Chaos.
You have a facilities manager running to 50 different rooms to manually set 50 different dials to 72 degrees. Eventually, human error guarantees that someone will set the break room to 65 and forget the conference room entirely.
Yeah, and that is duplicated configuration in a codebase. By extracting default args, Ang installed a central digital thermostat.
Right. You set the baseline configuration once at the top of the hierarchy, and every test suite inherits that baseline state.
If we connect this to the bigger picture, centralizing configuration is about establishing a single source of truth. Yeah.
When a test suite relies on 50 duplicated instances of configuration object, the sheer surface area for bugs expands exponentially.
Right. If the underlying args type changes in the future, say you add a new required parameter,
You suddenly have to hunt down and update 50 isolated instances of that object across your test files.
and if you miss even one of them, the compiler yells at you. Or worse, the test fails in a bizarre, cryptic way because it's running on a stale configuration state.
Exactly. By pulling default args out and making it the universal baseline, Ang ensures that future modifications to the system's configuration only require a single line change in the test suite.
That's huge.
Combined with the centralized logic in assertRight and assertSuccess, this refactoring drastically shrinks the maintenance footprint of the entire codebase. You are basically practicing defensive programming against your future self.
It's about designing a system where doing the right thing is actually easier and faster than doing the wrong thing.
I mean, a developer doesn't need to copy-paste a 20-line case statement anymore because typing assertRight is objectively faster.
And Ang concludes the journal entry by teasing the next installment. They explicitly state that the following post, presumably part 186, will demonstrate exactly how these two new helper assertion functions are utilized in practice within the test files.
It's a great cliffhanger for a technical diary. It perfectly illustrates that refactoring is a multi-step journey. The first phase is identifying the rot and building the correct architectural tools to excise it.
And the second phase is the actual application of those tools to clean up the implementation.
Right.
It also requires discipline. Once you build the centralized tool, you have to ruthlessly enforce its usage, or else you just end up with the new paradigm competing alongside the old copy-pasted legacy code.
Nobody wants that. Let's take a macro view of the journey we've unpacked today. We started with a system bogged down by its own defensive mechanisms.
A Haskell test suite suffering from the accumulated fatigue of doing things the brute force way.
Resulting in those sprawling, copy-pasted test files Aang described.
But the solution wasn't to write fewer tests. The solution was to elevate the level of abstraction.
Yeah.
By identifying the repetitive logic, the constant manual checking of either and parser result outcomes, Aang was able to design a structural bypass.
Those pattern-matching higher-order functions, assertRight and assertSuccess, acted as intelligent routers. They automatically unwrapped data, handled failures uniformly via the HSpec library, and executed the nested logic only when appropriate.
And tying it all together was the elimination of configuration drift.
Establishing default args as the single source of truth for the baseline state ensures the tests remain resilient against future architectural shifts.
It really is a masterclass in reducing cognitive load for the developer.
It fundamentally changes the experience of interacting with that code base. But before we wrap up this deep dive, I want to leave you with a final thought to mull over.
Okay.
A slightly provocative angle on this entire process. Throughout this exploration, we have aggressively celebrated abstraction.
Yeah.
We've championed the idea of hiding the messy, repetitive, unwrapping, and failure states inside these neat encapsulated helper functions to save space and streamline our reading experience.
The pursuit of clean code practically mandates it.
It does. But here's the lingering question. At what point does our beautifully simplified test code become so highly abstracted that we forget what exactly it is we are fundamentally testing?
That's a scary thought.
Think about it from the perspective of onboarding. If a new junior developer joins the team and opens a test file, and all they see are heavily customized functions like assertRight feeding into other bespoke helpers.
They aren't actually looking at Haskell anymore.
Exactly. They're looking at a domain-specific language, a custom dialect that your team invented entirely for the test suite.
And then the cognitive load shifts. You no longer have to understand the verbose code, but you now have to memorize the hidden mechanics of the abstraction itself.
Right. If we abstract the automated drone inspector's job so thoroughly that the human operator is just staring at a single green light on a dashboard all day, does that operator even possess the context to understand what a catastrophic rivet failure looks like when the green light finally turns red?
Wow.
It is a delicate balance between efficiency and opacity. It's something to actively monitor the next time you find yourself copying and pasting your way out of a problem.
Absolutely.
Look for the localized boilerplate in your own workflows. See if you can build a better routing mechanism, but make sure you don't abstract away the very understanding of the system you are trying to protect. Thank you so much for joining us on this deep dive.